Ever wonder about the magic that happens between a giant power plant and the outlet in your wall? Well, it all comes down to one incredible piece of tech, the generator. But how in the world do you take simple physical motion and turn it into the electricity that runs, well, everything? Let's get into it. What's really wild is that an electric generator is basically just an electric motor, but running in reverse. Think about it. A motor takes electricity in and gives you motion out. A generator does the complete opposite. You give it motion, and it spits out electricity. So the big question is, how does it pull off that amazing trick? So here's the game plan. We're going to start with that fundamental reversal, then uncover the magic of induction. After that, we'll build a virtual AC generator piece by piece, look at the kind of current it creates, and finally see how this machine powers our entire world. All right, let's start with that core idea, taking movement and somehow turning it back into electrical energy. The whole thing works because of a law of physics called electromagnetic induction. Now, the definition sounds a little technical, but the idea is actually pretty simple. You can create a voltage in a wire just by putting it in a changing magnetic field. And that word changing, that is the absolute secret sauce to everything we're about to talk about. So let's pull back the curtain on that secret ingredient. How does this so-called magic of induction actually work? Okay, picture this. You've got a wire and a magnet. If you just hold that wire perfectly still inside the magnetic field, nothing, absolutely nothing happens. But the second you move that wire so it cuts through those invisible magnetic field lines, poof, a tiny current is generated for a split second. Stop moving, the current's gone. It's all about the motion through the field. Okay, cool. So we've made a little spark of current just by moving a wire. But which way is it flowing? Does it just go wherever it wants? Nope, not at all. There's a rule for this. So how do we figure it out? Well, physicists came up with a super handy trick called Fleming's right-hand rule. You can literally do this right now. If your thumb points in the direction of the motion and your first finger points along the magnetic field, then your middle finger, bent at a right angle, shows you exactly which way the current will flow. It's a simple little hand gesture, but it's a super powerful way to see what's happening inside a generator. So what if we want to get more juice out of this? How do we make the electrical output stronger? Well, there are basically 3 knobs we can turn up. First, move the wire way faster. Second, get a much stronger magnet. And third, and this is the big one for real generators, instead of one wire, use a coil with hundreds or thousands of loops. More loops cutting the field means a way, way bigger voltage. All right, we've got the physics down. Now let's take those principles and actually build the machine itself. Let's assemble an AC generator. And here's the basic blueprint. At its heart, an AC generator is really just a coil of wire that we force to spin around inside a magnetic field. That spinning action is the motion input that gets the whole party started. Let's break down the main parts. First, you've got the coil of wire. That's the bit that spins. Next, you need the magnets to create the magnetic field for the coil to spin in. But, how do you get electricity out of something that's spinning without the wires getting all tangled up? That's where these last 2 parts are genius. You have 2 metal slip rings that spin with the coil. And then you have stationary carbon brushes that just press against those spinning rings, creating a constant sliding contact to pull the current out into the circuit. Pretty clever, right? Okay, so the machine is built and that coil is spinning. What kind of electricity are we actually making? Well, that brings us to the alternating current output. As that coil makes one complete 360-degree turn, the voltage it makes isn't constant. Instead, it rises and falls in this really beautiful, smooth, repeating wave. This is the signature of alternating current, or AC. It's called alternating because the current literally flows one direction, then reverses and flows the other way, over and over again. And believe it or not, this exact wave is what's coming out of the outlets in your home. Okay, so let's follow the coil for one full spin. We'll start here at position 1, where the coil is standing straight up. In this position, the sides of the coil are moving parallel to the magnetic field lines. They're just sliding alongside them, not cutting across them. And what's our rule? No cutting, no current. That's why the graph shows 0 volts. But now, a quarter turn later, we hit position 2. The coil is perfectly horizontal. Here, its sides are slicing through those magnetic field lines at the fastest possible rate, a perfect 90-degree angle. And that's where we get our biggest kick of voltage. hitting the maximum positive peak of our wave. We keep spinning. Another quarter turn brings us to position 3. The coil is vertical again, and just like when we started, it's moving parallel to the field lines. No cutting. So what happens? You guessed it. The voltage drops all the way back down to 0.
And the spin continues. At position 4, it's horizontal again, cutting those field lines at maximum speed. But look closely. Now the sides of the coil are moving in the opposite direction than they were at position 2. And because of that, our right-hand rule tells us the current reverses. We get another maximum voltage spike, but this time it's in the negative direction, creating the bottom part of the wave before it returns to 0 to start the whole cycle over again.
So this simple idea, a spinning loop of wire, is the foundation for almost every watt of electricity we use. Let's zoom out and see how this little machine truly is powering our world. See, in a real power station, you don't have some person turning a crank. You have massive turbines, things spun by high-pressure steam, or the incredible force of falling water at a dam, or huge wind blades. And the only job of those turbines is to spin these absolutely giant generators. The principle is exactly the same as our little model, just on a completely epic scale. Now, making the electricity is just step 1. To get all that power from the plant to your house without losing most of it along the way, the generator needs a partner in crime, the transformer. Generators and transformers are a total team. Right at the power plant, a step-up transformer jacks up the voltage to an incredibly high level for long-distance travel. Why do that? Well, it's a bit of physics magic. High voltage lets you send the same power with a very low current, and that low current means you waste way less energy as heat in the power lines. Then, right near your house, a step-down transformer brings that voltage back to a safe level for you to plug in your toaster. So, when you boil it all down, it comes back to this one simple, elegant idea. A generator takes in motion and generates electricity. And there you have it. That's the heart of our entire energy grid. The generator is that critical link, the machine that turns mechanical energy into the electrical energy that powers our civilization, which, of course, leaves us with one last, really big question to think about. We know that generators turn motion into electricity, but what moves the generators?